The normal distribution is one of the most powerful mathematical tools we will have in order to analyze our data in statistics. And fortunately, R has plenty of built-in commands that allow us to do everything we'll need to do with the normal distribution. R has two main commands built in. pnorm calculates probabilities given values. So if I want to take a z-score and put it in there, I do pnorm of z. That will give me the probability of finding a value below, less than, a certain z-score. Or I can take pnorm, I can give it a raw score, an x, a value there, and then give it the mean and the standard deviation of my normal distribution. And again, that will calculate the probability of being less than that x value. So pnorm gives me probabilities. The other big R command to deal with the normal distribution is qnorm. Qnorm takes in probabilities and gives me values. If I compute qnorm of p, then that will give me a z-value that has that probability of p of being less than it. Or if I do qnorm of a probability and then the mean and the standard deviation of that normal distribution, well, then it will find me an x value, a raw score that has that probability of being below it. So let's do an example. One thing that is normally distributed is the heights of adults. In the United States, the heights of adult men closely follow a normal distribution with an average height of 5 feet 9.3 inches, that's 69.3 inches, and a standard deviation of 2.94 inches. So here's a question I could ask. I say, what percentage of adult men in the US are shorter than 5 foot 7 inches? I can do this directly with pnorm. I can go to pnorm, I put in 67, that's the 5 foot 7 inches, 69.3 the average, 2.94 the standard deviation, and R will spit out 0.217, so that tells me 21.7% of adult men are shorter than that height. I can also do this by first computing a z-score. I can get my z-score by taking my value minus the mean divided by the standard deviation, so I've got 67 minus 69.3 over 2.94. That's a z-score of negative 0.782, meaning that 5 foot 7 inches is 0.782 standard deviations below the mean. So then I can take that and put that directly into pnorm. Pnorm of negative 0.782 gives me exactly the same number, 0.217. 21.7% of adult men in the US are shorter than 5 foot 7 inches. Here's another example. Same scenario, adult men, same mean, same standard deviation. What if I want to say, not below, remember all these R routines are programmed to give us probabilities below something. What if I want a probability above something? Well, that's easy. All I need to do is subtract the value from 1. If I've got this distribution and I find, well, there's a certain probability of being less than that, well, then to get the probability of being more than that, I just do 1 minus that, because you're either less than or below, either more than or less than any specific value. So, what percentage of adult men are taller than 5 foot 10 inches? Well, now I do 1 minus pnorm of 70, there's 5 foot 10, 69.3 the mean, 2.94 the standard deviation, and R gives me 0.406, 40.6% of men are taller than 5 foot 10. Or, similarly, I can compute the z-score first. Often that'll be useful. So there's the 70 minus 69.3 divided by 2.94 equals 0.238. My z-score of this is 0.238. So 5 foot 10 inches is 0.238 standard deviations above the mean. So I go to pnorm of 0.238 and I get exactly the same result, 0.406 or 40.6%. Let's do another example. What if, okay, so we got the same thing, heights of men, same mean, same standard deviation. What if I want to know the percentage of adult men who have heights between two values? In this case, between 5 foot 7 and 5 foot 10. How do I figure that out? Well, in order to do that, I need to use pnorm twice. Okay, so if I apply pnorm to the 5 foot 10 inches, to the 70 inches, then that will give me all the men who have heights less than that, but I don't want to go all the way down. I want to stop at 5 foot 7. If I apply pnorm to the 5 foot 7, to the 67 inches, well, that'll tell me the probability of being below that height. So that's the amount I want to subtract from the other amount. That's the amount I want to chop off of the distribution. So I do pnorm of 70, 69.3, 2.94, and then I subtract from that pnorm of 67, 69.3, 2.94, and when I stick that into R tells me that is 0.377. That tells me the probability of being in that range. The probability that the next randomly chosen guy to walk through the door will have a height in that range. Similarly, I can do this with the z-scores. We computed the z-scores just a minute ago, so I can do pnorm of positive 0.238 minus pnorm of negative 0.782, and I get the exact same number, 0.377, or 37.7% of adult men in the United States have heights in that range. Okay, now let's do an example with heights of women. Again, heights of adult women in the United States closely follow a normal distribution with an average of 5 feet 3.8 inches, 63.8 inches, and a standard deviation of 2.8 inches. So here's a question. Let's go the other way. What if instead of asking for percentages and probabilities, what if I start out with those and ask for values? So 90% of women are below what height? Or in other words, what height is the 90th percentile, the value that separates, that has 90% of women below it and 10% of women above it. From that, I use the command qnorm. Qnorm of 0.9, again, the mean 63.8, standard deviation 2.8, tells me that is 67.4. 90% of women are shorter than 67.4 inches and 10% of women are taller than 67.4 inches. Or I can get a z-score first. I can just do qnorm of 0.9. That tells me 1.28. So that means the z value is 1.28. 1.28 standard deviations above the mean is where that 90th percentile is. So I can compute that. That's the number of standard deviations above the mean. So the mean is 63.8. I take 1.28, multiply that by the standard deviation of 2.8. I'd add that to the mean 63.8, and I get the same result, 67.4 inches. All right, let's do a similar problem. What if I want to say, again, heights of women, there's the mean, there's the standard deviation. 75% of women are above what height? What's that height that has 75% of women above it and 25% of women below it? In other words, what height is the first quartile of adult women's heights in the United States? I can do this by using qnorm of 0.25. Notice that R is always working with probabilities of being below a certain value, so I use the 0.25. There's the mean, 63.8. There's the standard deviation, 2.8. I get 61.9 inches is the first quartile in adult women's heights in the United States. Or I can compute a z-score first. qnorm of 0.25 gives me negative 0.674. That's the z-score. Okay, so the z-score of the first quartile, this applies to any normal distribution. The z-score of the first quartile of any normal distribution is negative 0.674. And then I can convert this back to a raw score, an actual height. I take the mean, 63.8, and I add negative 0.674 times 2.8, the standard deviation, and I get the same thing, 61.9 inches. All right, so this is fun, this is cool. Now, what if I want to gather a sample from a population? What if I want to randomly select a sample of n items from a normally distributed population, and this normally distributed population has a mean mu, a standard deviation sigma? What will happen then? We're going to be doing this a lot in statistics. This is one of the most common things we're going to do in all of statistics. We gather a sample from a population. We're going to take the average of that, we call the mean of that sample, the average of our sample, we call that x bar, x with a line over it. So notice now we got two different means running around here. We've got mu, that's the average of the whole entire population, everything that's out there that describes the whole distribution. And then I've got x bar, that's the mean of my particular sample. If I did the study again, I would get a different sample and I would get a different mean x bar, but the underlying mean mu would be the same in both cases. Suppose I did this many times. I got many samples, and for each sample I get an x bar, a sample mean, and then what I would find is the interesting, cool, awesome, wonderful, amazing discovery is these sample means, all these x bars, would form another normal distribution, and we call this the sampling distribution. What we would find is if I made a histogram of all these different x bars, all these different sample means, I would find the sampling distribution has the same mean, mu, as the underlying population did. But I would find the sampling distribution has a smaller standard deviation than the population itself does. A sample mean, x bar, is much more likely to be close to the overall average. This is because if I just grab one person, well, I'm talking about, I don't know, the next man to walk through the door, well, it could be the person is unusually tall or unusually short or unusually far from average. But if I take the next, I don't know, if I randomly gather a sample of 100 men, Well, there might be a few unusually tall or short people in there, but most of them should be relatively close to average, so it's much more likely that my sample mean is going to be pretty close to the overall population mean. And what I find is the larger n is, the larger my sample size, the more things I've got in my sample, the smaller the standard deviation is, meaning the closer my x bar is likely to be the overall mean. And the magical equation that allows us to compute this tells me that sigma x bar, the standard deviation of all those x bars, is sigma, the standard deviation of the population, divided by the square root of the sample size. That's an amazing, interesting, powerful equation that we're going to be using a whole awful lot. Let's do some examples with that. Okay, suppose I want to study the velocities of galaxies. Astronomers have discovered that the Coma cluster, a galaxy cluster out there, contains over 1,000 galaxies. Each one of those galaxies contains hundreds of billions of stars in a great big beautiful spiral disk, and then they all orbit around each other in messy and complicated ways. And we find that the galaxies of this cluster, their velocities are distributed with a normal distribution. They have an average velocity of 6,925 kilometers per second away from our Milky Way galaxy, with a standard deviation of 1,000 kilometers per second. Here's a question. Suppose I randomly select 100 galaxies in the Coma cluster. What's the probability that we would get an average velocity of less than 6,700 kilometers per second? Okay, so now we're talking about the average of a sample mean. I go to pnorm, all right? There's pnorm. There's the value I'm interested in, 6,700. There's the mean, still 6,925. But now I'm talking about the average of a sample of 100. So notice I'm putting in something more complicated for the standard deviation. I don't just put in 1,000. That's the standard deviation of all the galaxies. Instead, I have 1,000 divided by the square root of 100. The square root of 100 is 10. 1,000 divided by 10 is 100. So now the standard deviation is a factor of 10 smaller because I'm talking about the average of a group. I put that into pnorm and I find 0.0122. That's very unlikely. That's only a 1.22% chance that we would get a sample of 100 galaxies with a mean velocity of less than 6,700 kilometers per second. Similarly, we could do this by getting a z-score first. Now notice we have a slightly different equation. On top, to get a z-score, we have our value minus the mu, but downstairs, in the denominator, I've got sigma divided by the square root of n. So I take 6,700 minus 6,925 over 1,000 over the square root of 100. I find that my z-score associated with this is negative 2.25. That speed, 6,700 kilometers per second, is 2.25 standard deviations below the mean. I put that into pnorm. Pnorm of negative 2.25 gives me, well, there's the same number, 0.0122, 1.22%. Let's do another example with this. Again, the Coma cluster, galaxies, same mean, same standard deviation. Suppose I randomly select 100 galaxies in the Coma cluster. There is only a 1% probability that we would get a velocity above what? Okay, so I want a value, I want a velocity where we would only have a 1% probability of being above it, and so therefore we would have a 99% probability of being below it. Remember, R is always wanting to deal with probabilities of being less than some value. So whenever I have a probability of being above something, subtract it from 100% and figure out the amount below it. So in this case, I do qnorm of 0.99. There's the mean, 6,925. There's that standard deviation divided by the square root of the sample size, 1,000 divided by the square root of n equals 100 galaxies. I put that into qnorm and I get 7,158 kilometers per second. Of all these galaxies, if I were to gather a sample of 100 of them, there's a 99% chance I'm going to get a velocity less than 7,158 and a 1% probability that I'll get a velocity above 7,158. Similarly, we can compute the z-score first. We can do qnorm directly on 0.99. That gives me a z-value of 2.33. Aha, so that means in order to get to the 99th percentile, I have to go 2.33 standard deviations above the mean. So I can convert this back to a raw score. I take my mean, 6,925, plus my z-value, 2.33, times this standard deviation divided by the square root of n, and I get 7,158 kilometers per second. So to summarize, pnorm is the R command, which takes values or z-scores as input, and then it spits out the probability of finding something smaller than this. Qnorm is exactly the opposite. It takes probabilities as input and then outputs values or z-scores that have this probability of being below that. A lot of times, oftentimes, what we're going to do is we're going to gather a random sample of n objects from a normally distributed population with some mean mu and standard deviation sigma, and we will compute the sample mean. We'll call the sample mean x bar, an x with a line over it. If we gather many, many of these samples, what we find is that all these x bars form a distribution, which we call the sampling distribution, and we find that the distribution of all of these is beautifully normal. The sampling distribution of many x bars will have a mean of mu, the same as the underlying population, but the important, amazing discovery is that the sampling distribution of x bar will have a standard deviation which is reduced by a factor of the square root of n, so that the standard deviation among all those x bars is sigma, the standard deviation of the population, divided by the square root of the sample size. That's an equation we're going to be using an awful lot.